This is lesson 8.3, day 4, solving trigonometric equations as general solutions. For the warm-up, please solve the trigonometric equation and find all solutions over the interval from 0 to 2 pi. Pause the video, and when you finish, turn it back on and check your answers. The solution is 2 pi over 3, pi, and 4 pi over 3. Pause the video if you need to check your work. All right, today what we're going to be looking at is a little bit more general. So when I look at cosine of theta being 1/2, I've talked about only those solutions that are between 0 and 2 pi. However, that's because the unit circle only goes from 0 to 2 pi. When I actually look at a graph of a function of a cosine that intersects y equals 1/2, you'll see that this will have intersections with infinite solutions because I can keep this graph moving on. So the solutions will occur in a very predictable pattern. So you can see that you've got 2 here in this cycle, 2 here, and 2 here, but there is a relationship as we move further on between this point here and this one here, and this one here, and this one here. But we do want to talk about, specifically at least in the beginning, the actual solutions that fall between 0 and 2 pi. So when I look at my graph, there we go. So I'm going to go ahead and cut those. So when I look at the unit circle, those two solutions occur at pi over 3 and 5 pi over 3. If I take those two graphs and look at them separately on the Cartesian coordinate plane, what I'll notice is that that first solution of pi over 3 repeats, and it repeats at a distance of 2 pi. The second solution, 5 pi over 3, it also repeats at a distance of 2 pi. So if I have repetition in my solutions, I'm going to have to come up with something that's called a general solution. All right, so it says how to write the general solution. So I have two unique solutions here, pi over 3 and 5 pi over 3. And the reason that I know that they are unique is that I can't create 5 pi over 3 from pi over 3. Additionally, I can look and see clockwise and counterclockwise, these values don't match up. So it's not like I can take 5 pi over 3 and create it by a multiple of pi or a multiple of 2 pi. So in other words, these are unique solutions that will generate multiple solutions. So I have to come up with a general solution that fits each of these. So here is how you write a general solution. Pi over 3 is unique, and since it generates multiples of that solution, what I do is I start by writing x equals pi over 3, which is the first solution. Any other solution is multiples of that, so I'm going to do multiples of 2 pi k, because I know that the solutions repeat every cycle of 2 pi. So the 2 pi is the distance where the solution will repeat itself. For pi over 3, I have the same relationship. I've got 5 pi over 3 as my initial value, and then I have these multiples of 2 pi where k is an integer, and I'll generate other values. Now let's say that I wanted to generate solutions, specific values along the cosine function. So what I would need to do is replace the k value in these equations with an integer. So I can replace k with a -1, a 0, a 1, a 2, and it would generate probably about 8 solutions, 4 from the first one and 4 from the second one. I could do this for any value I wanted. I could even put in a k equals 100. We generally do find that we do work with -1 to 2. Usually those will cover what we need. So if I replace the k with a -1, so what I'm going to do is I'm going to work in this particular equation and replace k with 1. Well, 2 times pi times 1 is just 2 pi, so I'm just adding those together. Use a common denominator, and you're going to get 7 pi over 3. So that's a multiple of pi over 3 that is a solution to the original equation. k equals 0, we'll generate the initial solution. Pi over 3 plus 0 is just pi over 3. K equaling 1, you substitute in, you'll have pi over 3 plus 2 pi times 1, which is 2 pi, common denominator, and you'll get 7, let's see here, pi over 3 plus, let's see here. So this one, actually this should have been a negative. Let me go back there. This one should be negative 5 pi over 3. There we go. This one will be your 7 pi over 3, like that. K equaling 2 will generate pi over 3 plus 2 pi times 2 is 4 pi. Common denominator. That generates 13 pi over 3. So now, I'm not going to rework out the problems that are over here on this other side. However, I want to show you what happens when you generate these values. So if k is negative 1, I can see I've got the negative 5/3. But if I had worked out the other side, I get negative pi over 3 for this second equation. And likewise, same thing here. This first one is from over on this left side. This pi over 3 is from the right side. And then here are the other values. Now what happens if your values are not unique? What happens in that case? There we go. So what I see here is pi over 4 and 5 pi over 4. You'll notice that they are opposite of each other in the unit circle, and they're equidistant whether they're clockwise or counterclockwise. That tells me that 5 pi over 4 is a multiple of pi over 4. I can just add pi to it. So to figure out that you have a repeating distance, you've got to look at these angle situations. In this case, because they're evenly spaced, I could write 5 pi in terms of pi. So it's not unique, so I'm not going to use it. I'm only going to use the pi over 4 to create a generic equation. So just like before, we've got this value in the first box that's going to be the initial value of pi over 4. But what you'll notice this time is it doesn't cycle through at 2 pi, it cycles through at pi, because I can see that I have a multiple of this, or adding pi to it. Alright, so we're going to go ahead and do some practice problems. So 2 sine of x plus 3 equals 4. I'm going to go ahead and solve for sine of x by subtracting 3 and dividing by 2. I'll get sine of x equals 1/2. If you go to your unit circle, those two values are pi over 6 and 5 pi over 6. And when I check those over in the circle here, pi over 6 and 5 pi over 6, I do find they're unique solutions. So I'm going to write two generic equations, pi over 6 plus 2 pi k, and 5 pi over 6 plus 2 pi k. Alright, so tangent theta equals 1. So let me go ahead and erase my unit circle values that I have here. So we're going to look for the values that come up with multiples or they're identical. So square root 2 over 2 divided by itself is going to give me that, as well as the negative version of that. Notice though that these two are opposite of each other. So even though I got x equals pi over 4 and 5 pi over 4, we already talked about the fact that 5 pi over 4 can be created from pi over 4. So I'm going to go ahead and do that as well. So what I have here is going to be x equals pi over 4 plus pi k, because it repeats itself every pi k value. Alright, number 3. We've got a two-step equation. We're going to add 1 to both sides and divide by 2. So ultimately we're going to get that the cosine squared of x equals 1/2. Take the square root of both sides. So you get that the cosine of x equals plus or minus 1 over square root 2. And then of course we rationalize that. That's plus or minus square root 2 over 2. So now that occurs 4 times in the unit circle. So it occurs, let me go ahead and write this down, at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. When you go up to the unit circle, what you're going to notice is that these are all opposites of each other. Like this. But furthermore, all three of the ones in the quadrants 2, 3, and 4 are multiples of pi over 4. We're just going ahead and adding pi over 2 each time. So we don't need to use anything but pi over 4 to create our general equation. So the general equation is pi over 4 plus pi over 2k, like that. So just adding on 90 each time. So the big question is, why are we using general solutions anyway? Well, what if we need to generate values still between 0 and 2 pi, but the period length is different than what we had been working with? So when I look down at this graph in part C, when I'm down here, here's what happens. That 2 pi changes the period. In other words, I complete a cycle in pi rather than 2 pi. So I end up with more solutions between 0 and 2 pi than I normally would. In order to do that, I need to come up with the general equation first and then apply the 2 pi to it. So we're going to do that now. All right, so where does sine pi equal 1/2? So we're going to ignore this 2 pi for a minute. And that occurred at two places, pi over 6 and 5 pi over 6. They are unique values, so we can generate general solutions for them. So the two general solutions would be pi over 6 plus 2 pi k and 5 pi over 6 plus 2 pi k. Like that. There you go. Now, in order for us to calculate any missing values of theta, we have to take the 2 pi and set it equal to each of these general solutions. So 2 theta equals pi over 6 plus 2 pi k, and the second one, 2 theta equals 5 pi over 6 plus 2 pi k. We're going to solve for theta. We're going to divide both sides, or you can divide all the way across by 2 in all cases. So I get theta equals pi over 6 divided by 2 is pi over 12, and then the 2's cancel here, so we have pi k. For the second one, we're going to have 5 pi over 12 plus pi k. Those are the general equations for this specific trigonometric function. But now they want us to figure out the actual solutions between 0 and 2 pi. So part D says use the k values to generate that. So you can start with the negative if you want to, just to see if it'll work. So when I put a -1 in here, well, this would be negative pi. And pi over 12 plus a negative pi is going to be negative, so that's not going to work at all. It'll go into the negatives and it won't fit within the domain restriction from 0 to 2 pi. And the same thing happens here as well. So you can skip the -1. The k equals 0. Well, if I put 0 in here, it'll generate the pi over 12. So pi over 12, and it will also generate the second one, which is 5 pi over 12. So those both work just fine. So now we're going to try k equals 1. So I'm going to put a 1 in here, so I have pi over 12 plus pi. And simplifying that is going to give you 13 pi over 12. And on the second one, 5 pi over 12 plus pi is going to give you 17 pi over 12. And both of those work as well. When you try to do k equals 2, when I put a 2 in for k, I get 2 pi right here. 2 pi plus anything else that's positive is going to exceed the domain restriction. So I'm going to skip 2 because it won't generate a value. So I have 4 solutions, and I'll write those out. So theta equals pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. So number 5. We ignore the 2x temporarily, and we're only looking for cosines of square root 2 over 2. And those occur where, let's see, so cosine x equals square root 2 over 2, and that occurs where x is equal to pi over 4 and 7 pi over 4. And if you look at those on the Cartesian coordinate plane, they're unique. So we're going to take the 2x and set it equal to the generic equations for both of those. So 2x equals pi over 4 plus 2 pi k, and 2x equals 7 pi over 4 plus 2 pi k. Divide by the coefficient all the way across. You can work them simultaneously or you can work with them independently. That's up to you. So over here on this left-hand side, we get x equals pi over 8 plus pi k. And this one, you get x equals 7 pi over 8 plus pi k. So k equals -1. In both cases, we'll generate negative values that fall outside. So skip that. K equals 0 will always generate the first two solutions within the range, pi over 8 and 7 pi over 8. At least for this problem it will. Those both work. If k is 1, we have pi over 8 plus pi, which is going to be 9 pi over 8. And then we have 7 pi over 8 plus pi, which is going to give me 15 pi over 8. Those both work. And then we need to go see if k equals 2 will generate any values. Now, if we look at our general equation, if we put a 2 in here, that's 2 pi on that last term. 2 pi plus pi over 8 is going to exceed the value, and it will for the next one as well, so those are skipped. So your solutions for this one, there are 4 of them. We've got pi over 8, 7 pi over 8, 9 pi over 8, and 15 pi over 8. All right, number 6. So we're going to ignore the argument of x over 2, and we're just going to look where all of the sign values first are. The sine of x is equal to 1/2. There we go. And that occurs at pi over 6 and 5 pi over 6. So we're going to go ahead and take the argument and set it equal to the general rule. So x over 2 equals pi over 6 plus 2 pi k. And the second one, x over 2 equals 5 pi over 6 plus 2 pi k. You're going to multiply both sides of this by 2. So you get x equals, and 2 times pi over 6 is pi over 3, and 2 times 2 pi k is 4 pi k. The second one, we'll get x equals, multiply this side by 2, you're going to get 10 pi over 6, which is 5 pi over 3, and 4 pi k. We need to generate values between 0 and 2 pi, so we're going to go ahead and attempt to do that. Now for k equaling -1, if you put a -1 in here, that's going to be -4 pi, and your result will be a negative no matter what for both of the generals, so skip those. If k equals 0, you generate pi over 3 and 5 pi over 3, and both of those fit within the domain. If k equals 1, well, at this point you become too big, because 4 pi times 1 is 4 pi, plus pi over 3 way too big, and the same thing for the second one. So for this particular problem, you only generate 2 values. So your solutions for this one are pi over 3 and 5 pi over 3. Okay, this is the last problem that we're going to work. So we're going to look at those general solutions first. So we want to find where tangent of x equals -1, and that occurs at two places. It occurs at 3 pi over 4 and 7 pi over 4. And we want to make sure that those are unique. So we've got 3 pi over 4 and 7 pi over 4. Those are not unique. They are opposite from each other. That means 7 pi over 4 can be written using 3 pi over 4. So we're only going to create one generic equation. So we have 2x equals, and we're going to use the 3 pi over 4. And it looks like because these are a distance of pi from each other, it's multiples of pi. So pi k, like that. And we're going to divide everything by 2. So we have x equals 3 pi over 8 plus pi over 2k. So now we're going to go ahead and check values to see what happens. So let's try k equals -2. So if we use k equals -2, we'll have 3 pi over 8 plus, so pi over 2 times -2 would be -pi, and that is going to give me a negative result, so we can skip that one. So if k equals -1, we'll get 3 pi over 8 minus pi over 2, like that. And if we do common denominators for this, we'll also get a negative value. So we'll skip that one. So k equals 0. That will generate our initial value of 3 pi over 8. So that works. K equals 1. That will generate 3 pi over 8 plus pi over 2. We'll use a common denominator. That will generate 7 pi over 8. And that actually works. Then if we look at k equals 2, we'll have 3 pi over 8 plus pi over 2 times 2 is going to give me pi. That's going to be 11 pi over 8. That one works as well. So now we're going to go to k equals 3, because it looks like it's a possibility that we'll keep finding other solutions. So we'll have 3 pi over 8 plus pi over 2 times k is 3 pi over 2. Common denominator, this will be 12. So now we have 15 pi over 8. That also works. So we're very close here to the end. So if you try k equals 4, you have 3 pi over 8 plus pi over 2 times 4, which is going to be 2 pi. And you can see now that we've reached our limit, so this is a skip. So our solutions for this particular problem are going to be pi over 8, 7 pi over 8, 11 pi over 8, and 15 pi over 8.